origin of black hole superkicks. He's currently setting up, and then we'll see how this works. He's local, so this will go easily, and you have 25 minutes for the talk, 5 minutes for the questions. You see my umbrella here that I'll shake at you if you're too late. Yeah.
Yeah, I'll move in just a second. So if you have something that just one second. Okay. Cool.
Just a second.
All right. Can you hear me on Zoom? Hi, everybody. My name is Anuj Kankani. I'm a third-year graduate student at West Virginia University. Today I'm going to be talking about work I'm doing with my advisor, Sean Williams, on black hole superkicks. So it occurred to me as I was making this presentation that there are probably people here at this meeting who were involved in the original superkick papers. It's pretty cool. But for those of us who aren't, black hole superkicks were kind of one of the big numerical discoveries that came after all of the breakthroughs in the early 2000s. And what they found was that in cases of binary black hole mergers, where the two spins of the black holes were opposite and aligned along the orbital plane, that when the final black hole emerges from the merger, it receives a significant kick out of the orbital plane. So there's a nice little cartoon picture I grabbed from actually an Astrovite article on the early superkick papers, if anyone wants to check that out. And so if we take two black holes orbiting in the XY plane, this is kind of what I'm going to use throughout this presentation. If their spins are also opposite along the XY plane, then that final black hole is going to receive a big kick or velocity in either the plus or minus z direction, depending on the spin orientation. And so obviously when this was discovered, people wanted to know how big can the kick be? And it turns out it can be pretty massive. So I think in pure superkick cases, quasi-circular pure superkick cases, there was something like 4,000 kilometers a second, and then it can be boosted by combining things like a hang-up effect and eccentricity and so on. And there was a recent paper that looked at head-on cases of two black holes just colliding with each other. And if you extrapolate to the maximally spinning case, it ends up being something just under 10% the speed of light, which is kind of insane when we're talking about, supermassive black holes and not some low mass ejected material or particle or something. And so obviously, when you have a supermassive or any black hole going thousands of kilometers a second, that's going to have some pretty significant astrophysical consequences. But then there's also that big caveat of, hey, we also need spins with at least one component along the orbital plane, and ideally as opposite as possible. And so astrophysically, do we expect that to happen? And I'm not going to talk too much about the astrophysics today, but the good news about superkick simulations is that these results are mass insensitive. So they apply as much to stellar mass black holes as they do to supermassive black holes. And when you have such a wide range, you also can have very wide environments. You have globular clusters, you have black holes at the centers of galaxies, you have accretion disks, you have gas-poor, gas-rich environments, all of which will affect the spins of the black hole differently, and all of which will affect the probability of actually ending up with a superkick. And so, of course, superkicks aren't binary either. It's not either you get super fast kicked or you don't get kicked at all. It's a gradient. And so because of that, you can also get a wide variety of kind of consequences. You can get off-center quasars. You can get a black hole that's kind of kicked from the center of the galaxy and then starts to sink back down due to dynamical friction. Or you can get black holes that receive that obtain like the escape velocity of the system. So it can be completely ejected from the environment, the globular cluster or galaxy it's in. And obviously that's not going to affect just the local environment of a black hole, but also if we consider like second and third generation mergers and how black hole mass evolves, well, if a black hole is completely ejected, it can't really participate in future mergers. And then so people are also starting to make gravitational waveform models that can incorporate superkicks. So Vijay Verma used, I believe, it was a NR surrogate model to look at one of the LIGO detections. And they determined that at something like the 90% confidence level, that final black hole was either hit of at least 6 or 700 kilometers a second. And so if that black hole was in a globular cluster, it almost certainly would have been ejected, because those escape velocities are usually just a few dozen kilometers a second. But today, I'm going to talk more about the physical dynamics that are at play at Superkicks, and kind of how do we connect simulations with theory and kind of physical picture of what's going on. And so when we think about what is a superkick, the obvious answer is black hole goes super fast out of the orbital plane. But there's kind of more to it. So one of the key signatures is asymmetrical radiation. Essentially, more radiation goes one way than the other. So it's often been called a radiation rocket, because just like, pointy end up, pointy end down, black hole goes one way, excess radiation is emitted in the other direction. So if you look at the 2-2 mode, which is biased towards the North Pole, and the 2-2 mode, which is biased towards the South Pole, you can see clearly one direction receives a lot more radiation than the other. But so while superkicks basically happen at merger, there's also other cool physics going on during the in-spiral. And so if we, again, take black holes orbiting in the XY plane, that's where almost all of their motion is going to be. But there's also a little bit of bobbing in the plus or minus z direction, in and out of the orbital plane. And so this was, I think, first explained, at least heuristically, by Franz Pretorius in one of his review articles. And if you consider kind of the two black holes orbiting in a plane here, in picture B, both black holes are spinning. And so black hole 1 spin exerts a frame dragging effect on black hole 2, which pushes it into the page. And black hole's 2 spin induces a frame dragging effect on black hole 1, which pushes it into the page. And then so both black holes go into the page here, and then half an orbit later, the reverse happens, but they're both being pushed out of the page. And so during the in-spiral, even though pretty much all of the motion is in the XY plane, or in the orbital plane, you'll see a little bit of bobbing in and out of the plane, regulated by the orbital time scale. And so obviously people are interested not only in how fast black holes go, what are kind of the astrophysical consequences, but also what is the actual theory and frame dragging effects going beyond this. And so people looked at this analytically using Post-Newtonian theory. They looked at it using numerical relativity simulations. And so before I kind of get to the work we did, I think it's useful to kind of talk about what people have done already. So this picture I showed you that was produced there is actually slightly misleading. This is actually out of phase by half an orbit, just due to how frame dragging effects work. It's really an S cross B. But essentially, people have looked at this in different ways, and some of the finer details may vary a little bit. But the broad picture essentially is that there are frame dragging effects in play. Consider kind of spin orbit forces. Black hole 1 exerts a spin orbit force on black hole 2. Black hole 2 exerts a spin orbit force on black hole 1. They both point kind of in the same direction, so there's bobbing in and out of the plane. So you may ask, well, isn't to the extent that some sort of Newtonian action-reaction law is obeyed, why is there any motion? Shouldn't they be an equal and opposite reaction? And they pointed this out in the paper as well, that if you actually split up the spin orbit forces into kind of loosely labeled action-reaction terms, they don't cancel out, that there is a net force on the system. Now, and that net force causes the bobbing. Now, if there's a net force, there's also a net momentum. And so in order to conserve total momentum, we have to account for that extra momentum we've added to the system to the spin orbit forces. Where is that coming from? Well, the common solution that was taken was to incorporate momentum stored in the field. So it's kind of analogous to that common E&M problem you guys probably did undergrad at grad school that motivates like why you talk about the field. Just like that in GR, they said if you also account for the momentum stored in the field as well as the momentum stored in black holes, then total momentum is still conserved, and you can explain the bobbing as these spin orbit forces. Now, so this was done in post-Newtonian theory at the 1.5 p.m. level. And the problem in general relativity, of course, is that you can't really discriminate between momentum stored in the black holes and momentum stored in the fields. And so if you really want to do that, you have to resort to gauge-dependent values. And of course, then the question becomes, well, can you trust a gauge? And I'll talk a little bit more about that. But at least during the in-spiral, you have this picture of spin orbit forces causing the bobbing, momentum stored in the field, this constant exchange, and this little dance going on. But then what causes the kick, right? Quasi-circularity is breaking down, you have the plunge and the merger. Well, so there was a Caltech-Cornell collaboration a while ago that produced a bunch of papers that looked at this numerically. And what they argued was that at merger, you essentially have really strong frame dragging forces pushing the system in one way. But then when these two black holes merge, you get this common horizon that forms. And so this common horizon basically eats or incorporates the momentum stored in the field, which pushes the black hole in the other direction. But then the horizon shape is changing and it's incorporating more momentum, which causes the black hole to get pushed in the other direction. And essentially, the important part is that during this merger phase, the system is undergoing these massive swings in acceleration. It's going thrown in one direction, then it's thrown in the other direction, and they're competing effects. And so while merger itself is really large acceleration, once it's done, because these effects are kind of destructive, the final black hole acceleration, while large, is much smaller than what you see during merger. And so that is kind of what happens. That's kind of the picture that's been explained so far to explain superkicks, right? During a spiral, you have these spin orbit forces, which are causing the bobbing, and then you have momentum that's stored in the field, and then when you go to merger, you have a combination of these spin orbit forces and the common horizon eating that momentum, and that's what's causing the kick. Well, there's some questions I think that can be asked, and maybe some of these have simple solutions that obviously people here are a lot more knowledgeable than I am. But you can ask, for example, what happens to momentum stored in the field in scattering cases, where two black holes approach each other, they're exerting these spin orbit forces, there's momentum stored in the field, but then as they go away, what happens to that field momentum? Does it get radiated away? Is there some deformation? I don't think it's completely clear what happens there. But I think a bigger question is kind of, when you do these simulations, you're using gauge. All numerical relativity simulations are done in a gauge. And so if you look at, for example, the coordinate data, those are gauge-dependent results. And can we trust the gauge? Because if you want to see, at the end of the day, what we want to know is how fast is the black hole going and what direction is it going? What's the true black hole motion? And you can do that by just looking at, AH finder, puncher tracker, output data, and you see these massive swings during merger. But alternatively, you can also calculate the radiation, momentum lost in the radiation, and you see it behaves completely differently. It's smooth, unidirectional, and doesn't see any of these massive swings. So if you use this kind of field momentum frame dragging picture, sure, you can explain this massive swings that you see in this gauge-dependent data. But at the end of the day, if you have a black hole that's going really fast, accelerating in one direction, then going in another direction, then going back in another direction, why is the radiation so only really going in one direction? Interestingly, at the end, both values actually converge to basically the same result. But during the merger, there's clearly two very qualitatively different pictures being painted, depending on if you trust gauge-dependent coordinate data or radiation. So kind of just stepping back a bit and thinking about what exactly do we see in a superkick. Like I mentioned, it's a radiation rocket. You see black hole going one way and the radiation going, excess radiation rather, going the other way. But I think the question is it the black hole going one way that's causing excess radiation to be emitted the other way? Or is it excess radiation being boosted in one direction that then by conservation of momentum is causing the black hole to go in the other direction? Essentially, what is actually being frame dragged at merger? Is it a black hole being frame dragged? Or can we alternatively say that the radiation is actually being frame dragged and boosted in one direction, and the black hole motion is a consequence of that? And then of course, how do we connect simulation and theory, right? Do we trust the gauge? Are we looking, should we use radiation at infinity? Is that a more accurate picture of the true motion of the black holes? And then finally, is the kick a continuation of the in-spiral bobbing, or are we seeing different physics become dominant? If during the in-spiral we say there's the spin orbit frame dragging force, which we can look at in post-Newtonian theory, of course, during merger, everything breaks down, and so we can't really use that same post-Newtonian theory. So is it the same forces at in-spiral that are still dominant at merger, or do different frame dragging effects become dominant? And so a couple of years ago, my advisor built what he calls the backward one body, or Bob model, and it's essentially a way to model the gravitational radiation for the merger ring down portion of a black hole in spiral. And it uses a one body approach, so it's effectively a little, well, the effective one body name, but it uses properties of the remnant black hole to model the merger ring down radiation. And the really important part to understand about Bob is that it's all about the light ring. So the physical picture that Bob paints is that in this one body model, you have, your one body, and you have some perturber that's coming towards the one body. All that matters is the moment that the perturber crosses the light ring. That's when all of the merger ring down radiation is going to be generated. Now, why do we see merger and then ring down? Why do we see this time gap? Well, these disturbances are going to be created with different frequencies and have different angular momentum. So they take different amounts of time to leave the light ring. So for example, the merger radiation would be the first to leave the light ring, and therefore reach us the first. The what we'll call the ring down radiation will have different angular momentum, different frequency, and take longer to leave the light ring. And that's why you see this time delay. And so what we're going to do is, can we use kind of this backwards one body picture to explain superkicks? Because of course, while in spiral is interesting, superkicks are really all about that merger radiation. And so if we say that the perturber crossing the light ring is creating all the radiation, and then what we can do is say, well, what's the effective frame dragging effect at the light ring? Is this radiation being boosted in one direction? And then if we can calculate essentially the asymmetry in the radiation when the perturber crosses the light ring, how is that radiation being boosted? We can then get the kick velocity. And so a really simple calculation you can do is, this was NR simulations done by Lowster and Slow. I'm not trying to pronounce that, sorry. Essentially, what they found was that pure superkick simulations are kind of when the spins are along the orbital plane, but there's also a hang-up effect, which essentially maximizes the total radiation emitted by the system. So if you only have one component of the spin along the orbital plane, you can actually get even larger kicks. And so essentially, if you have your spin angled with respect to some theta to the orbital angular momentum, for every spin, there is some theta angle that maximizes the kick. And so what they did was they essentially used NR simulations and then created some fitting form, and they showed that, hey, at these spins, this is the maximum kick. Well, you can use this Bob light ring picture to analytically just determine what is this maximum theta at every spin. And so you say, perturber crosses the light ring, you can integrate the net frame dragging effect over the light ring, and essentially calculate how is the radiation being boosted. And from that, you can see, without really needing any NR, you can match the NR results pretty well, especially at low and medium spins. At higher spins, it starts to diverge a little bit. It may just be a lot of simplification without this Bob calculation, or also just higher spin fitting formula, maybe something breaking down there. But essentially, it suggests that really it may actually be the radiation that is being frame dragged at merger. And then because this radiation is being frame dragged, essentially excess radiation goes one way, And by conservation of momentum, the black hole goes the other way. And then so we can also ask, well, what about the in-spiral bobbing then? If we're saying at merger, the radiation is being frame dragged during the in-spiral, are we also, is also the radiation being frame dragged, or are we seeing these kind of classic spin orbit frame drag, black hole effects? And so first off, please ignore that phase difference in these plots. I'm pretty sure that's just a bug in my code, but in the attempt to just have not have false results, we'll show that phase difference. But essentially, it would appear that at least during the in-spiral, that it is a spin orbit frame dragging of black holes that is dominant, because you can at least you can just argue that there is so much more radiation being generated at the merger than the in-spiral. You can say that even if you take age-dependent coordinate accelerations, it's still a factor of 100 times greater than the kind of acceleration you would get by looking at the momentum lost in the radiation. You can kind of take just the spin velocity data from NR simulations, plug it into the PN terms, since this is all during the in-spiral, you can look at 1.5 and 2.5 PN terms. And you see the magnitudes agree quite well, and even in the PN, this spin orbit frame dragging in the in-spiral is much, much larger. So it would suggest that it really is two different regimes, that during the in-spiral, you have this frame dragging of the black holes, so to speak, but then at merger, you have kind of frame dragging of radiation. And so how exactly does the system transition between these two effects? I think, frankly, that's still an open question. It's not completely clear. Obviously, during the in-spiral, if you're talking about momentum stored in the fields, everything averages out over an orbit. But then as you break that quasi-circularity, and you transition to frame dragging of the radiation, what exactly happens to that momentum stored in the field? Is it radiated away? Is it transferred to some other part of the orbit? It's not entirely clear. But kind of the big picture results is that if we use this backwards one body model, it would argue that at merger, it's the radiation that's being frame dragged, and that's what causes the kick. It has a bonus that you don't really need to rely on age-dependent simulation results. You can get the same results as you do from NR simulations, but just analytically, which is quite nice. And then, of course, like I mentioned, the in-spiral itself does seem to be dominated by the frame dragging of black holes and the classical spin orbit forces. And yeah, mostly.
What is the time for questions? So, start with, are there any questions in the room? Apparently, lunch is competing with your question time. There might not be lunch outside. So, I have maybe a question. So, I haven't really worked anywhere in the Superkicks at all.
Yeah.
And the ones that I had in mind is all in the plane, and then it gets ejected in the plane. But I presume if the thing is bobbing, it can also go out of the plane and just capture all of this correctly.
So kicks in general are generated by any asymmetries like mass asymmetry and things like that, and that can result in plane kicks. What we call super kicks are specifically out of the plane kicks that you spin pretty high.
Okay, and then this all works. And then something else, which I guess came up to me, I very vaguely remember that tens of years ago when this all first came up and people thought, okay, it's sloshing inside of the field, that there was a presentation by Sangrella who thought about how this might work. Is this connected, or is that really only relevant for the in-spiral? And then after
so they used kind of a hidden momentum picture in which they also argued that the in-spiral and the kick are kind of two different mechanisms. But they're essentially, if I remember correctly, it's again, the kick was being generated by momentum that gets stored during the in-spiral. Whereas here we would say it's two completely different things going on, and there's no real connection between the two.
So you add an extra bit of information to this now to properly interpret this.
Yeah.
It's maybe a bit easier to handle. And yeah, something sloshes, I don't know what's going on.
Yeah, there's again, if you trust gauge, you trust things, simulations like that.
Cool, very nice. So I guess the correct reason is you would generally prediction you want to use this one in some sort of population synthesis code for.
Yeah, so I mean, one, just if we have this picture, can we at least predict something to show that picture is right? But then ideally, yes, like, can you just show without having to resort to some NR fitting simulations? Can we just, this is kick velocity, this is distribution, and this is right?
Yeah, very cool, very nice. So that is something more done. Okay, yes.
Great talk, thank you. I wanted to ask you if, so I don't remember you saying if this was just primordial black holes or astrophysical.
So this, I mean, astrophysical black holes in the sense that, I mean, these simulations are, of course, mass insensitive, like Einstein told me, I suppose would apply to any black holes of any mass, so I don't see why this couldn't also apply to primordial black holes, since they'll also have some mass and some spin,
Right.
and so the same effect should be at play.
And so if these were to be modeled specifically for primordial black holes, would you ever be with investigating if they would have gravitational wave signatures or counterparts?
I mean, so how how the primordial black hole spin would be affected, I have no idea in terms of like early on in the universe or how they get affected by primordial black holes that still exist today by the environment. If they do have spins that are compatible with the superconductor configuration, then yes, there would be some gravitational radiation as for its detectability. I'm not sure, but yeah, the same physics, I don't see a reason that the same physics would apply.
Thank you. Oh, Peter?
Yes, so I remember back when this stuff first came out, that it was kind of unclear whether as physically you can actually get those configurations.
Yes.
The rotation spins. So has there been some more projects figuring out those?
I will say not so much, as in if you look it up, like the library of Superkicks, it's still from the early 2007 papers. Of course, the big question is kind of I would argue if you have like some accretion disk that's going to align the spins with normal angular momentum, you're probably not going to get Superkicks. Right? If you have like a globular cluster or more random interactions. And the thing I like is, yes, it's probably not occurring super commonly in the universe, but they're cute. So even if they're not super common, they pack a punch.
Okay, very good. Then there are no more questions, and I don't think I saw a question online. Let's thank the speaker once more. Great. And then just so for those in the room, lunch hopefully outside.